Hello everyone, my name is Ilham Alwardi. I'm from Morocco and I belong to Faculty of Science Moulay Ismail in Meknes. First of all, I would like to thank the organizing committee for giving me the opportunity to participate in this conference and to present my work entitled on the static frictional contact problem with thermal and electrical Signorini conditions in thermo-piezoelectricity. This work is a collaboration with the professors Al Hassan Ben Khaira, Rashid Fakhar, and Yusuf Mandini. The outline of my presentation is as follows. I will begin by describing the physical framework and presenting the mathematical formulation. Following that, I will give the weak formulation. Then I will show the main result of this presentation, the existence and uniqueness result. Later, I will present the numerical approximation. Finally, I will conclude by discussing some conclusion and perspective. So we consider a thermopiezoelectric body occupying in its reference configuration an open and bonded dominated omega, which is a subset of RD with a regular boundary noted gamma. The boundary gamma has two partitions. The first one is divided into three disjoint measurable parts correspondent to the thermal and the mechanical conditions, and the second part is also divided into three parts correspondent to the electrical conditions. In the domain omega, we suppose that the body is subjected to a volume force of density phi sub 0, a volume electric charge of density phi 0, and heat source Q sub 0. On the zone gamma D, we suppose that the body is fixed, so the displacement field vanishes there. Also, the electric potential and temperature are zeros respectively on gamma A and gamma subcapital gamma subcapital D, cap gamma sub N. We also suppose that a surface fraction of density Fn acts on gamma n and a surface electric charge of density phi b is prescribed on gamma b. And in the contact zone, we suppose that the body comes into a static fractional contact with a thermally and electrically conductive obstacle. So, according to this physical framework, the fourth mathematical formulation will be described as follows. Here, the following equations are respectively the equations of stress equilibrium, the equations of electric field, and heat conduction's equation, where sigma refers to the stress tensor, div sigma is the divergence of the operator sigma, and capital D is the electric displacement field. Also, the following equations represent the constitutive law of the material, which characterize the properties of the material, where the operator which appear in these equations are a physical operator. For example, Matkal for capital F is the nonlinear elasticity tensor, beta is the electric permittivity tensor, and etc. The linearized strain tensor is noted by epsilon and in small deformation is given by this form. Also, U, phi, and theta are respectively the displacement field, electric potential, and temperature field, which are the now of our problem. Moreover, to complete our mathematical model, we need to take into account the boundary conditions on each part of gamma. So, we have a Dirichlet conditions on the Dirichlet zone for the displacement field, electric potential, and temperature field, also a Newman conditions on the Newman zone. And concerning these last two conditions on the contact zone are the characterizing conditions of our problem. The first is called the Signorini's condition that take into account the action of the obstacle to the body in the normal direction. And the last condition called conditions of friction that take into account the action of the obstacle to the body in the tangential direction. So, what does Signorini conditions mean in our situation? In our case, we have chosen the classical Signorini conditions. for the displacement field to ensure that the obstacle can't penetrate the body when they come into a contact. Also, we assume that the electric displacement and the heat flow are unilateral from the obstacle to the body to ensure that the displacement field and the temperature of the body do not exceed those of the obstacle. And for the last conditions along to the tangential direction, we have used a version of no-local column friction law. This condition means that when the body is in contact with the obstacle, the latter exerts a tangential force on the body that does not exceed a certain threshold called the threshold friction given by this quantity. Therefore, this condition physically means that as long as the norm of tangential stress is less than the friction threshold, then the body does not slip on the obstacle. So the tangential displacement is equal to zero. And when this threshold is reached, then the body starts to slide horizontally on the obstacle, and its displacement occurs in the same direction but in the opposite movement of the obstacle. Therefore, the fourth mathematical formulation of our model is to find the displacement field, electric potential, and the temperature field satisfying the following equations and the conditions. Now I will derive the weak formulation, but firstly I will introduce some notations. So we use the following standard notations for the Liebig and Sobolev spaces. Also, the Dirichlet conditions allows us to define the following closed spaces as follows. These spaces are real Hilbert space with their inner products and associated norms respectively. On the other hand, the conditions on the contact zone helps us to define the following closed convex subsets for the admissible displacement field, electric potential, and temperature field respectively. Also, by Sobolev's trust theorem, we have the following inequalities. And since we have supposed these two conditions, then Karn and Frederick Poincaré inequalities also hold. We need also to make some assumptions on the data. So we have the following conditions and regularity on the data of the problem. Next, by using Ree's representation theorem, we can define the following elements as follows. Therefore, by using the previous notations, standard procedure based on Green's formula and some mathematical manipulation, we arrive at the following weak formulation of the problem capital V, which is capital P, which is a system coupling of an elliptic quasi-variational inequality for the displacement field and the two elliptic variational inequality for the electric potential and temperature field, where G is the functional of friction, and it is defined by this form. Then our main result has been stated as follow. So suppose that the following assumptions hold. Then if there exists L star strictly positive such that the following inequality hold, then the variational problem has a unique solution. So the proof of this theorem is classical, and it is based on the argument of elliptic quasi-variational inequality and the Banach fixed point, and they will be conducted in several steps. Sorry. So, as a first step, let's start with the first step. So, let's zeta equals zeta 1, zeta 2 in V times W be given. Then the variational problem can be reduced to the following intermediate problem, not the PV sub zeta defined as follows. So to solve this new problem, we will start by introducing the following notation. So we consider the product space, not the capital X given as follows. Together with the inner product and the associated norm, we also define the operator A and the functional G and the elements of F capital F sub zeta by the following equalities. Then we have the following equivalent results. The problem PV sub zeta is equivalent to find x zeta satisfying the following inequality. And we have the following existence and uniqueness results. For any zeta in V times W, the problem PV sub zeta has a unique solution. So the proof of this lemma is classical, and it is based on a result of elliptic variational inequality of second order. So to achieve this, it is sufficient to show that the operator A is strongly monotone Lipschitz continuous. Also, the functional G is a proper convex Lipschitz, and there exists a positive constant alpha such that the following inequality hold. So the two results together ensure that the problem PV sub zeta has a unique solution. So for the second step, we consider the operator lambda defined as follows, and we have the following result. The operator lambda has a unique fixed point. So the proof of this theorem is of this lemma is based on the result of Banach fixed points. So it is sufficient to show that the operator lambda is a contraction operator. And as a final step, now we have all the ingredients to prove our main results, the existence and uniqueness of the solution of the variational problem. So for the existence of the solution, let's set zeta star be the fixed point of the operator lambda, and we denote by x sub zeta star the solution of the variational problem PV sub zeta, and in particular for zeta equals zeta star and the definition of the operator lambda, we find that the x sub zeta star is solution of the variational problem. And concerning the uniqueness of the solution, it comes from the uniqueness of the fixed point of the operator lambda. And this is completes the proof of theorem 1. Now I am going to present the numerical approximation. So the main objective of this part is to investigate the finite element approximation of the variational problem and to derive the error estimate of the approximate solution. So let's start by introducing the following notations. Here omega is assumed to be a polygonal domain. To H is denotes the finite element triangulation of omega bar, and the capital P sub 1 is the space of polynomials or of a global degree less or equal to 1 in each omega A. Also, we consider the following three finite dimensional spaces defined as follows, approximating the spaces V, W, and Q. And we also introduce the following non-empty finite dimensional closed convex sets of the admissible discrete displacement electric field and electric potential and temperature field defined as follows. Where H is her H is the parameter of discretization, and it is strictly positive. Then the discrete approximation of the variational problem is stated as follows. So on the approximation of theorem 1, we can find that the discrete problem has a unique solution, And we have the following convergence results. The solution of of the approximate problem converge to the solution of the variational problem strongly as h tends to zero. Now we will focus on the error analysis between the solution of the variational problem and the approximate problem. So let us denote by x and the xh the respective solutions to the problems PV and PVH and the PVH, and assume that the assumptions of theorem 1 hold. Moreover, under some additional regularity assumptions, we have the following optimal order estimates, where C is constant, strictly positive, independent of each. So, to prove this theorem, we will begin by establishing the following CS tips inequality, which is given by the following theorem. So, under the assumption of theorem 1, the following error estimate is obtained as follows. So, the proof of this result is based on the data of the problem and the Cauchy-Schwarz inequality. So the result obtained in this theorem is important for deriving the optimal order of the convergence of the convergence. So to achieve this, in addition to the assumption of theorem 1, let us consider the following pairwise linear interpolation of u, phi, and theta respectively. And also we consider that the following additional conditions holds. Then by using standard finite element interpolation error estimate, we have the following approximation. Therefore, by combining these results with the results obtained in inequality 41, then we get our main results, and this is conclude the proof of our main results. So to close my talk, I will mention some conclusion and perspectives. In this work, we have investigated a static frictional problem involving a deformable thermo-piezoelectric body in contact with a thermally and electrically conductive obstacle. And in small deformation, we formulated the problem in both strong and weak forms and established the existence and uniqueness of the solution. Also, we investigated a numerical approximation to the variational problem using the finite element approximation. These analyses include the demonstrating the existence and uniqueness of discrete problem along with an error estimate results under some regularity assumption. And as a perspectives, despite the complexity of the numerical solution of this kind of problem, it becomes a challenging and open problem. Also, we can extend the static case studied in this work to the quasi-static and the dynamic cases. And thank you for your attention.